Okay, so we'll get started here. So we are now into chapter 5, all right? And chapter 5 is, what's chapter 5 all about? It's about, I'll read you the, no, I will not read you the first page of chapter 5. It's something about bales of cotton. No one cares. Sorry. So chapter 5 is about rational expressions. And so instead of just looking at polynomials, now we're looking at ratios or fractions of polynomials. And we want to see what we can say about those. How do you solve equations involving them? You know, what can you say about their domain? These kinds of things. What was the domain? Do you remember? So first of all, just the definition. What's a rational function? So definition, f of x is equal to p of x over q of x, where p of x and q of x are polynomials. Makes f of x a rational function. So that's what a rational function is. A rational function is a function whose formula is given by the ratio of two polynomials. And what's the domain of a rational function going to be? So you tell me, what's the domain of f of x going to be in this case? I'll say the domain of p of x over q of x, just to be more to the point here. It's going to be x such that what? Such that, what breaks this formula? What makes the formula not make sense is division by 0, right? So the domain is just x such that q of x is not equal to 0. So that's the domain. Okay, so let's look at a few examples of finding domain. Start out relatively simple. F of x equals to 3 over x minus 1. You're like, is 3 a polynomial? Yeah, a number is a polynomial. It's a kind of silly polynomial, but a constant function is a polynomial of like the most basic type. So this is a rational function. What's its domain? X such that what? We need q in the denominator here, right? To be not equal to 0, right? X minus 1 not equal to 0. So in interval notation, you're like, oh, I'm happy about that. I've missed interval notation these weeks that we've been away from it. I was so hoping we could go back to interval notation and talk more about interval notation. Nothing makes me happier than talking about interval notation. Thank you, sir. But no, said no student anyway, ever. So this is minus infinity to 1 unioned with 1 to infinity. See, because what the condition above looks like on the number line is like x is anywhere, right? But the one thing x can't be, x is not equal to 1, right? So you've got everything like over here to there for this piece, right? And then everything to the right of 1 over here for that piece. So that's the domain. But again, you could also write it just as x such that x is not equal to 1. Example 2. Suppose we have f of x is equal to x minus 3 over, oh, I don't know, x squared minus 25. What's the domain of this function? So we need x squared minus 25 to not equal to 0 for x to be in the domain, right? Now, what is this? This is x minus 5 times x plus 5, right? So when could this be equal to 0? If we put this equal to 0, that tells me what? X is equal to either 5 or minus 5, right? So those are the troublemakers. Those are the points we have to throw out of the domain. So the domain of f is x such that x is not equal to plus or minus 5. Now, we could write that in interval notation if we wanted, right? But this is a perfectly good notation for the domain, so let's just... Do you want me to write it in interval notation? I mean, I can, but... All right, so your book has some questions. It says, find all numbers for which the rational expression is not defined. So that's a fancy way of saying, find the numbers you got to throw out of the domain, right? Which is really just the problem of finding the numbers which gives you division by 0 for the formula, right? All right, so enough about that. We can, I encourage you to try the homework on this. I think you'll see that you can do it. The main thing is, in order to understand where the denominator is 0, you have to, factor it, basically, right? I mean, there's more interesting examples. Here, I can do another one. I'll stop here, though. You could have something like this, right? F of x, 1 over x plus 1, plus, x over, I don't know, x squared minus 2. So this one here, we have, f of x not defined when either x plus 1 is equal to 0, right? Or x squared minus 2 is equal to 0. Either one of those is going to get us into trouble with the formula, right? So we have to throw out, this of course gives you what? This gives me x squared equals to 2, which we can solve to give us x is plus or minus the square root of 2. And this one, of course, gives me x equals to minus 1. So we need to exclude minus 1, the square root of 2, and also minus the square root of 2 from the domain. Okay, so let's now turn away from domain and talk about how to simplify and to work with rational expressions. All right, so the discussion of domain for polynomial functions you probably don't remember because there's really nothing to talk about with polynomials. What's the domain of a polynomial? Like, which real numbers can you plug into the formula for a polynomial? You're doing what? You're squaring, cubing those numbers, and you're multiplying them by real numbers. The fact of the matter is, the formula for a polynomial, it doesn't face division by 0, so you can just, the domain for a polynomial function is just all real numbers. So it wasn't, we'll ask questions about that sometimes on homework or a test or a final or something, but it's not, those are not tricky questions. And I don't think these questions are too tricky either. They're just, you got to think through them. But there's actually something to think about. So let's talk about algebra for rational expressions. So Here's some problems from your book. It asks us to multiply the expression by the given form of 1 to obtain an equivalent expression. Do not simplify. So let me just say, these are the rules, right? So I think there's two big ones. The one is that if we have A over B, maybe there's really three big rules here. A over B times C over D. We multiply A times C, and we multiply B times D. So when you multiply two fractions, you just multiply numerator times numerator, denominator times denominator. That's it. So that one, rule number one, that's pretty easy. I think we don't have too much trouble with that. The other one concerns something a little bit sneaky, which is compound fractions. So if I have A over B divided by C over D, sometimes people call these complex fractions, but I object to that terminology because for me, complex is something more interesting. So this is I call this a compound fraction or a fraction of fractions. Other people might call them nested fractions. So how does that work out? Well, this works out to, the rule is upstairs stays upstairs, but the downstairs of the downstairs is upstairs, which is kind of a funny house, you know? You go into the sub-basement and then you're back upstairs again. That's kind of weird. And then B goes down here and C goes down there. So the numerator of the denominator stays in the denominator. The numerator of the numerator stays in the numerator. But the denominator of the numerator goes downstairs, and the denominator of the denominator goes upstairs. Some examples of this, to maybe make it less mystical. If you have 1 over 1/2, this, of course, is equal to 2. So how many halves are there in 1? There's 2 of them, right? So this 2 flips upstairs, and you could, so this is really 2 times 1 over 1, you know, which is 2. Or if you like, we could do something like 1/3 divided by, oh, I don't know, 7/6. So the way this works is, let me make this 1 into something other than 1, like a 2. Okay, so the 2 stays upstairs, the 6 goes up here, the 7 stays down there, the 3 joins it. What's that?
I would just say then the 3.
Then the 3. And so what you got, well, maybe it simplifies, I don't know. What's this? 2 times 3 times 2 divided by, well, 7 times 3. So I guess we can cancel the 3's and we get 4/7. So that's one of the fundamental things we can do with fractions is we can look for common factors in the numerator and the denominators. If we find a common factor, we can cancel it, okay? So that's rule number 2. What's rule number 3? Rule number 3 for working with fractions, I would say, is make a common denominator to add. Okay, so if we have A over B plus C over D, a lazy way to add these is just to cross multiply. So A times D plus B times C divided by BD, right? That's how we can add fractions. I say that's a lazy way to add fractions because it can make the calculation needlessly complicated, right? So like here's an example of this. If I have, oh, I don't know, like 2 over 9 plus, you know, I don't know, 10/3. Well, then if I use this rule above, I do 2 times 3 plus 10 times 9 divided by 9 times 3. That's my cross multiply to add fractions method, yeah? And that's kind of a big number, right? That's 96 over 27, yeah? Right? Now, what's a better way to add fractions is to do what? Put it in your calculator. You're not wrong, but that won't help us gain insight into how to do these things with polynomials. Oh, but well, okay, but you're right, but this is the problem, is because these numerical calculations are what guide your intuition for the corresponding polynomial calculations. So if you don't know the numbers, you're at a disadvantage for the thing that comes next is the problem. But it's okay. I mean, we're going to get through it, but I understand what you're saying, and you're not wrong in terms of like you can use a calculator to do these, right? But my point to you is to add these in a less, so this is just very clunky. The better way to do this is to look for the least common multiple of these two numbers. What's the least common multiple of 9 and 3? Yeah, 3 times 3 is 9, right? So 9 is the least common multiple of 3 and 9. In other words, what we want to do is we want to take 2/9. We want to take the 2/9, and then convert this third to 9th. How do we do that? We multiply by 1 in the form 3 over 3. See, by multiplying that fraction by 3 over 3, we turn this into a 9th as well. And that's the thing, is we have to have a common denominator to add the fractions. So, I mean, that's what this formula does, is it makes the common denominator b times d, which in this case was 27. But we could make do with a much smaller common denominator for this numerical example, namely 9. And so what you got here is you got 2/9 plus 30/9, also known as 32/9. So see, by using the least common multiple, when we add the fractions, we get a nice answer at the end. Now you're like, well, I could still use my calculator, because if you're wrong, not wrong. If you plug 96 over 27 into your calculator, it should simplify it to 32 over 9, did it? It did, cool. So, but there's a corresponding polynomial example where your calculator won't do that simplification, right? All right, so this is just a quick review of the basic arithmetic we have for fractions. All of these basic arithmetic steps we can also put into practice for rational expressions. So like all of these things are still true when we're working with functions of x. So let me do an example. So if I, for example, what my number? 4. Okay, thanks. Suppose I wanted to add, let's see here, 3 over x plus 1 plus x over x minus 2. So if I want to add these two fractions, all right, what I do is I use my rule number 3. So what I'm going to do is basically cross multiply. You can think about it. 3 times x minus 2, all right?
Could you just go ahead and say 3x minus 6?
You could. And then, but I'm going to do it this way because I want to emphasize what's going on here. X times x plus 1. But you're absolutely right. That would be 3x minus 6. I do not disagree. I would not deny you that. Certainly not. And then the denominator here is x plus 1 times x minus 2. This is using rule 3. Okay? And we can clean this up a little bit like you were just telling me. This is 3x minus 6 plus x squared, right? Plus x, using all that polynomial multiplication we learned back in chapter 4, right? And the denominator, oh, you're going to multiply it? x squared minus x minus 2? So you could multiply the denominator out. A lot of times, actually, it is better to have them factored. Like the denominator being factored is actually better, but we could multiply it out if we wanted. That's true. But notice we can collect terms. So we've got what we got. So I'm actually gonna go back to the denominator being factored, if you don't mind. This is x plus 1 times x minus 2. You're like, well, that was kind of pointless. Well, yeah, I mean, a little bit. But I prefer to have the denominator factored if I can, all right? Because if it's factored, I can immediately tell you what the domain is. You know, the domain is all numbers which are not equal to minus 1 or 2. And that's also manifest here. And we got what? We got x squared plus 4x, right? Minus 6. So there you go. I mean, that's pretty, maybe we could factor that. We could probably factor the numerator. But it's not particularly pretty. It involves square root of 10 and some stuff, right? So, I mean, for your book, this is the answer, I'm pretty sure, or the one above, you know. So you might have a problem where it says add these fractions, simplify the result, if possible, right? Let's work in an easier example. Example 5, multiply. Do not simplify. So if we have x plus 3 over x squared plus 8, and we multiply that by x cubed over x cubed, what happens? We get x to the 4th, yeah, plus 3x cubed. Well, 2 plus 3 is 5. So x, yeah, x to. Oh, okay. So x to the 5th plus 8x cubed, yeah? There you go. That would be an example multiplication, right? Let's look at an example that uses rule 2. All right, let's look at a rule 2. What's that? You don't like rule 2? Well, maybe rule 2 doesn't like you either. Did you ever hear that? Ever somebody say that? Like somebody says, I don't like the rain, and then somebody's like, well, maybe the rain hates you. I don't know, I've always found it to be a delightfully absurd response. 2, rather 6. So this time I'm going to say rewrite as simple fraction. I'm not sure your book uses that terminology, but I think it's a good term. A simple fraction is a fraction which is just, you know, one numerator, one denominator. It's not a compound fraction, right? So here's what I'll look at. Something like, I don't know, x squared divided by x plus 1 over x minus 2 divided by x cubed. All right? Okay, so how's this go?
X squared is 2 and 5.
Yep, x squared times x cubed.
X plus 1, x minus 2 combined.
Very good. So we would get x to the 5th over, x plus 1 times x minus 2, which we could multiply out, but we don't have to if we don't want to, all right? There you go. So, yeah, I know 2 is a little intimidating, but if you just,
It's easy.
it's not bad. You just got to be aware of what you got to do, right? Um, let's look at some examples where we simplify. So simplification examples, what they are is basically undoing the steps we just did. You know, I mean, the goal is to use the 1, 2, and 3 to simplify the irrational expression. So let's look at some examples. We'll start out with some really kind of simple ones. So these would be like from section 5.1. Start real simple. Number 17 is 15y to the 5th divided by 5y to the 4th, which I'm going to change to x's. 15x to the 5th divided by 5x to the 4th, because I'm trying to work in variable x, but your book does like to change the letter, doesn't it? So, which is good, but I think it's also good for us to use one letter in lecture, just to make sure our understanding is. I don't want to burden you with other letters in the middle of lecture, okay? Not too much, anyway. So what we do here is we divide the numbers. 15 over 5 is 3, right? And we have x to the yeah, this is, well, the way this works is 5 minus 4. So I guess there's a rule I should have mentioned to you. Rule, like 1 over x to the n power is equal to x to the minus n power. So if we have a positive power in the denominator, we can rewrite it. So like this is x to the 5 times x to the minus 4. See, because 1 over x to the 4th is x to the minus 4. And then if we have x to the a times x to the b, we get x to the a plus b. So these are the laws of exponents here.
So your final answer would it be that, or would it just be 3x?
You caught some kind of cow cold? Is this some sort of equine?
Allergies.
Oh, just allergies. How can you be like rodeo and do allergies? It's pollen. It's not animal. Go for it. The math will still be here. Welcome back. Sorry about your allergies. I know it's that time of the year, isn't it? So, so here's I just wrote another example. I haven't worked it out yet. I wrote the problem statement. I haven't worked it out yet. This is like number 29 from section 5.1, and then this one's number 33 from section 5.1. So if we can understand these, we'll be a good ways towards understanding how to do a lot of problems in this chapter. Like the mechanics of these questions, there's a lot in the mechanics here. So let's finish example 7, right? So we 1 over x to the 4th is multiplication by x to the minus 4, and then we add exponents when we multiply like bases like this. So this is 3x to the 5 minus 4, otherwise known as 3x. So this rational expression is just a funny way of writing 3x. Okay, there's definitely a simplification there. I think we can all agree. Now here, we're also supposed to simplify. So remember that factoring we did? Well, more factoring here. So can we factor x squared minus 9x plus 8? How does that factor? But if I do plus 8, then I'll get a minus. I think you want minus 1 and minus 8. But you're on the right path there. How about the denominator? Does that factor? I'm starting to feel like I copied this problem down wrong. There's supposed to be a minus 4. This was supposed to be a minus 4. That makes it more interesting. Like, if I don't put the minus there, then this is hard to factor. But if the negative... If I do negative... Okay, so plus 4, right? And minus 1. Right, so that... Aha! Look at that. See that? This cancels with that. And what are we left with? Right. So we have simplified the rational expression by factoring the numerator and factoring the denominator and canceling out like factors. It's also worth noting that by doing this simplification, the natural domain of the simplified expression is actually a little bit larger than the domain of the original expression. The original expression, you had to omit what? You had to omit 1 and minus 4, right? Either 1 or minus 4 makes this formula here blow up, you know? But the boxed formula only has trouble with minus 1. Minus 4. So the trouble with 1 is gone because we canceled it in some sense. But anyway, that's more a comment for people who are going on to like calculus and junk, or pre-calculus. But so let's go on here. Let's look at example 9. Now here, the instructions are to multiply and simplify. Now, I would say that you could also simplify then multiply. I mean, sometimes it's smarter to simplify before you multiply. Let me show you what I mean. So this is x to the 4th times what? Well, this is 5 times x plus 2, right? So when we multiply fractions, we multiply numerator times numerator and denominator times denominator, right? But I can go ahead and factor the numerator. I can pull a 5 out of this. See, that's 5. So it's really x to the 4th times 5 times x plus 2, you know? I can do what? Down here, this I can factor a 3 out of that one, right? So this is 3 times x plus 2 times 5 x to the 7th. Well, look at that. So you see what happens? We've got a common x plus 2. So when we're multiplying fractions, it's always smart to factor the fractions before we multiply and look for any cancellations. If we had just multiplied the numerator and multiplied the denominator without thinking, then we would have still had to factor what we multiplied. It would have made work for us. You know, this is much easier. So be smart about it. Look for things you can cancel before you actually multiply, so to speak. Anyway, so what we got here is, what we got? 5x to the 4th over, oh, wait a minute. What am I doing? What am I doing? What else can I cancel? The 5s, right? Aha! Death to 5. All right, so there we go. Sorry, such violence. So we have 1 over, yeah. Right, and we can do better than that, right? Because that is 1/3 times x to the 4th times x to the minus 7, right? Which is 1/3 times x to the 4 minus 7, which is 1/3 x to the minus 3, which we could also write as 1 over 3 times x cubed. So sometimes you want to write your answer just using positive exponents. So like I like that as an answer, but honestly, the one right above it is also like a totally legit answer here. So there you go. That's some sample calculations from chapter 5. We'll do more as we continue on. I'm sorry your allergies. Hope they get better. Yeah, hopefully I should have the test graded by Wednesday. That is the plan. What's that? You won't be here Friday?